Hello, my name is Max Newman, and today I will give a talk on the Diploid Moran model conditional on its pedigree. This is joint work with Waitong Lewis Fan and John Wakely. Um, so, what's the general structure of the talk? Well, the basic outline is I'll introduce the Moran model and introduce the problem that I want to talk about pairwise coalescence times, conditional on the pedigree, and the relationship this has to ancestral graphs. So, what's the diploid Moran model? Well, it's a diploid monoecious panmictic population of constant size with discrete time steps and overlapping generations. So what happens is that at each time step, there's exactly one reproductive event and exactly one offspring is produced and another individual is killed. That's what preserves the population size. And so now I can describe what these reproductive events look like. Well, like I said, this is a model with selfing. So with probability alpha n, we have a selfing event. So that's single child is chosen at random, and it chooses a single parent at random from the previous time step, right? And then, of course, you can have a non-selfing event or splitting event. So with probability 1 minus alpha n, we have a splitting event. And you can see in the second time step here, a single individual is chosen, and it has two parents, right? So this model has appeared in the literature before. In the case where alpha n is a fixed constant, strictly less than 1, it appeared in the paper of Linder, and where it's 0, it appeared in the paper of Cron-Lejeune. And the chromosomes follow Mendelian randomness. So the central object of study here is essentially pedigree. So what's the pedigree? It's just a graph explaining the reproductive relationships of the population backwards in time. So, each child is connected by an edge to its parent or to both its parents in the case of a splitting event. And each individual is connected to itself if it persists in the population to the previous time step. So if you look at the first individual here, they existed in the previous time step, so there's an edge connecting to itself in the previous time step. And also the third individual is the child of the second and of the sixth individual. So there's edges connecting it to its two parents. And similarly, in the second time step, the fifth individual is the child of the third individual. And so there's two edges emanating from that child to its parent. And what's happening beneath the pedigree is the population level process and how the genes are actually being inherited. And as I said, this follows Mendelian randomness. Well, how does this Mendelian randomness affect things? Well, if you consider taking a sample of two genes from the population and you trace backwards in time to the time that they coalesce, even if you know the pedigree, even if you know the history of the parentage of all the population, it's still random, right? So knowing the pedigree isn't enough to know the coalescence time, right? Uh, so we're interested in understanding the limiting distribution of this coalescence time. Um, and you can see here two examples of where the pedigree is the same, and yet the coalescence time is different, right? So you see in the first time step, the third individual is the child of the fourth. In the second time step, the fourth is the child of the second and third individual. And that's the same for both of these. But what's actually happening at the gene level is different, right? That's where the Mendelian randomness generates randomness for the coalescence time, even conditional on its pedigree. So what's the classical approach to understanding the limiting distribution of the conditional coalescence time? Well, it's kind of to average over all the pedigrees, right? So what's the average behavior of this coalescence time? It's given just by averaging over all of these conditional times, right? For an appropriate time rescaling, in this case, what's called a C1, which is the probability that two genes from two distinct individuals coalesce in a single time step. With that time rescaling, the classic approach is to average over all of these random pedigrees. And so you can do that. And we have this simple result which says that alpha n converges to alpha between 0 and 1 inclusive. Then the limiting distribution, when you sample from two distinct individuals, is just an exponential with time rescaled in this way. And this time rescaling, this 2 over 2 minus alpha, has appeared in the literature in a number of different places. Appeared in Pollock, Nordborg and Donnelly, Mollet, recently in Kogan et al., and elsewhere, not only in the context of selfing, but also in the context of recombination. Right. So, but this is wrong. Uh, this isn't a theoretically sound approach to coalescent theory. So why is that? It's because the sampling structure implicit in these classical coalescent models is that each locus has its own pedigree, as if they were sampled from independent populations. We know real populations, there's a single pedigree, right? The two loci from the same individual, uh, they should be linked by the fact that uh, the parentage of the population is the same for both of them, right? And that's not true for classical models. So the proper way you should approach this is to look at conditionally independent realizations, right? You should uh, look at everything under the assumption that they have a common pedigree. And so how do you say this mathematically? Well, essentially you look at the distribution of the coalescence time, again with a time rescaling of n squared in this case, but uh, conditional on knowing the pedigree. So assume as if you knew the pedigree somehow, and you knew the individuals from whom you sampled, what should that distribution look like? That's the more theoretically sound approach to coalescent theory. And well, what's the naive thing you could sort of do? Well, if you take these two sample lineages from two individuals, these belong to the pedigree, which is a random graph. Well, what if you just look at the subgraph of all the possible trajectories of these lineages? That is to say, at every outcrossing, the sample lineage could go left or it could go right. Um, and when they overlap, sample lineages will coagulate, they'll come back together. What's the structure of this graph, right? Uh, well, you might think that if the rate of outcrossing, which is 1 minus alpha n over n, is comparable to the rate of coalescence, which is the time rescaling we're using, uh, then you should get a meaningful limiting graph, right? So if this quantity 1 minus alpha n times n converges to some finite number, then you should expect that you get a meaningful graph. And in fact, you do. This is what our theorem says. It says that if you have this finite limit, then in fact, this discrete time graph with an appropriate time rescaling, again, it's the C1 time rescaling, converges to a particle system G lambda, where each particle fragments at rate lambda, and each pair of particles coagulate at rate 2, right? And that might seem a bit mysterious. What kind of process is that? Turns out it's not mysterious at all, right? It's just an ARG, an ancestral recombination or ancestral selection graph. So when the outcrossing rate decays like lambda over n with the population size, the structure of the fragmentation and coagulations of the trajectories of the sample lineages, of all the possible trajectories, behaves exactly like an ancestral recombination graph, which is why we call it just an ancestral graph, because it's really tracing all of the possible ancestral lineages backwards in time. And so if all of the possible trajectories of the sample lineages uh, just behave like it follows each fragmentation, each edge emanating from a fragmentation with equal likelihood, and it follows the coagulations in probability 1, it should look exactly like a random walk on the ancestral graph. And in fact, that's exactly what we find, right? So what's the distribution of the coalescence time conditional on knowing the pedigree and who you sample from? Well, if outcrossing rate remains comparable to the coalescence rate, which is that n times the outcrossing rate converging to some finite lambda, that's exactly what you get. You get the coalescence rate of this random walk on the random graph. The ancestral graph is the limiting distribution, right? And what we also find is that alpha n converges to some alpha, including 1, but the outcrossing rate far outpaces the coalescence rate, then in fact, the classical approach is robust. That is to say, it's actually a good approximation for the coalescence time. So now, what do these things look like? It's kind of strange to think that the limiting distribution will actually be random itself. Normally, we think of random variables as having a deterministic distribution that you sample from. Instead, these things have random distributions. And what do these distributions look like? Well, on the left here, you can see the CDF for a standard exponential rate 2 random variable. It's nice and smooth. But even for moderate lambda, like lambda equals 5, you have this strange jumps. They're jumping with random sizes at random times, and they don't look much like the standard exponential. And in the most extreme case, when lambda is equal to 0, it jumps from 0 to 1 according to some exponential rate 2 time, right? So it jumps at this random time all the way up. It's like a random Heaviside function, right? Um, and so what does this tell us about the relationship between sampling across loci, right? So you can characterize how much this process differs. The conditional time differs from the classical time. In fact, you find that the variance of this conditional time is exactly equal to the covariance of conditionally independent times from two distinct loci in two distinct individuals. And it's given by this nice formula that decays like 1 over lambda. And because actually we found this connection to ancestral recombination graphs, the ancestral graph. In fact, this is also identically equal to the probability that the two times are the same, which is interesting, right? So you have this nice interpolation between a really random Heaviside CDF, this stochastic distribution, to a nice deterministic distribution as lambda goes to infinity. The sort of heuristic explanation for that is that because lambda is so large, the number of branches that you get in the ancestral recombination graph get huge. And when things branch many, many times, you really don't know where your two sample lineages are. So things sort of average out in that way. You have the sort of uncertainty grows very quickly as the number of branches grow, right? And what's really interesting is that actually this appears to be quite robust to the limit, right? So this is a nice simulation done by John Wakely, where even for pretty big lambda, like 100, you can see that there can be significant jumps in the CDF, that these distributions really don't behave quite like the standard exponential model, and that we think you should really try to account for that when trying to measure these coalescence times. Right, you can see that the rightmost, where the lambda is equal to 1, it really looks nothing like an exponential. You can some of these jump very quickly all the way to 1. And others have this nice staircase behavior. You can see for lambda equals 10, you have something sort of in between, right? So the bigger lambda gets, the more regular these sort of become. All right, now these are sort of incomplete collection of papers that have sort of pursued this perspective. There's this Wakely paper in 2012, Tukin, who found robustness for Hanning models, Wilton paper, and very recently, paper of Diamantidis about bursts of coalescence with large families. And that's all I really had to say. I would just, so thank you.